Okay, we are on lesson 7.3, and the title of it is Anti-Differentiation by Parts, but typically we call it Integration by Parts. So in antiderivatives, we have a couple of rules. We have power rule, and we recently learned U substitution. And this is a third method to allow us to integrate something that is a little bit more wacky, especially when the two parts or the parts in the integration is very, very difficult to see the relationship, right? So when we have U substitution, you typically have two trig functions. One is the derivative of the other, or if you have a composite function, you are able to see the derivative of a part of it in the other part of the integration. Integration by parts is useful when the two parts are not related at all. So let's say we're combining an e to the x function, an exponential function with a trig function, or a polynomial function with an exponential or logarithmic, or a sine inverse function with something else. So typically it's two of them that are not the direct derivative of each other, then we have to use the U substitution. So how does that work, right? So the U substitution starts with our composite function, our chain rule, right? With our product rule. So here we have a product. We start with a product. When we take the derivative of a product, right, you have the product rule, you have the derivative first times the original of the second, plus the derivative of the, keeping the original function of the first and the derivative of the second, right? So that is a rule that we know, product rule from when we took derivatives. Okay. So then how do we prove the formula we're going to use? We first then take the integral of both sides. Now remember, on the right-hand side, you have this addition problem. So because we are taking the integration of it, we're able to split it into two integrals, right? Because of the addition in the middle. So that's really nice. What is the key point here is that the integral will get rid of the derivative here. So on the left-hand side, you're now left with f of x times g of x, right? And then the other sides, the integrals won't go away. So we are now cleaned up looking like this, okay? And then we subtract one of the integrals over. So we subtract one of them over. So we subtract it, and I mean, it really doesn't matter which one, but because for the sake of our formula, it is best to go ahead and subtract this one, right? And then now let's name it, instead of naming it f and g, because it's just a lot more to memorize, well, kind of up to you, but we shorthand it into two functions, a u and a v. So we shorthand it into u and v, right? uv minus v du is equal to the integral u dv. So that's how this integration by parts comes around. So how it comes about. So you have your integral of u dv, that's this part right here, is equal to the function u and v, okay, minus the integral of v du, minus the integral of v du. So yes, you have to memorize this. This is the formula for integration by parts. So what is tricky here is to figure out what of your original integral, which part of it should you set up as your u and which part should be the dv. And yes, kind of like U substitution, if you don't set it up correctly, your integration won't work. So you kind of have to do, again, a bit of a guess and check. You have to be open-minded to try, but of course, we'll give you a lot of hints on what you should try to do in these cases, right? So typically, once you have this set up, your integration by parts, your second integral here, let me clean this up a little bit. Your second integral here would be a lot easier to integrate versus what you had originally. And that's the whole point of this integration by parts, is that this new setup, the new integral should be a lot easier. Okay, so we start off with a problem like this. Number one, x times e to the 2x dx, right? So here you have two functions. You have your first function of x, and you have your second function of e to the 2x. Now, typically, if we were using u sub, we would set the exponent there, the 2x, to be my u and go ahead and take the derivative. But if you had done that, you will see that the x will actually not be there. So that x outside is kind of it's kind of in our way. So that's why we have to use integration by parts. So typically what you want to do is you actually want to use the more difficult function as your dv, but it has to be something that you can take the antiderivative of, all right? So keep that in mind. So what we do here is we set up the left side, the x, as my u, and then we set up the dv as my e to the 2x dx. Okay, now you got to do two things. You got to do derivative because you need to find du, and you need to find v by taking the antiderivative. So if you did du, if you take the derivative of u, on the left hand side here, we will get, taking du, we get dx, right? Because du dx, you take the derivative of u, left side is du, the right side is dx. And then for dv, you now go backwards. You take the antiderivative. Keep in mind that e to the whatever is still e to the whatever, but because of this 2x up here, this 2 up here, you're taking the antiderivative. It's going to come out as a reciprocal. So your v is going to be 1/2 e to the 2x. Okay. Once you have these four parts, you have your u, you have your du, you have your dv, and you have your v, then you can plug it into the formula. The formula says it is going to be u, right? You start with u is x, times v is 1/2 e to the 2x, minus the integral of v is 1/2 e to 2x, and then du, that's your dx here, right? Again, even though it may not seem like it, but the second integral is much more doable. You can actually do this one. You can first take the 1/2 outside because it is a coefficient, and then it's just integral of e to 2x dx, which you did right here. This is the antiderivative. You have that already. So that's why my next line looks simple like this, where it has, when I clean up the first term, which is x over 2, e to 2x, and I pull the 1/2 outside, and this is my integral of e to the 2x dx, right? And then I clean that up. This is where you put the plus c. At the very end, you put the plus c. So because these are, right now, these are indefinite integrals, we'll put the plus c at the end, which is right here, right? So the last piece is just clean up. I'm going to clean this up and make sure that I have all my terms a little bit clean. Okay, so you have x over 2, e to 2x minus 1/4 e to 2x plus c. Some books will like you to factor out the e to 2x. It is not super necessary. You can actually leave it like this in individual terms. So it's really kind of up to you. Here I gave you a little hint to remind you of what I just said. We're going to, typically what we do is we need to guess what the dv is first. And dv is usually the one that you try to go for, right? You want the antiderivative of dv, so then you make the dv as complicated as possible, but you need to still be able to integrate it because you're going to take the antiderivative of dv to get the v. And then typically the u is a lot easier because you're just taking the derivative of that. So it's a little bit easier to take derivative of rather than taking antiderivative of dv, okay? All right, so something like this. So something like this, e to the x cosine x. So whenever e to the x is paired up with a trig function, this is something that happens very typically, and there's quite a bit of algebra involved. So let's take a quick look, all right? So first of all, in these cases, there is no more complicated. Well, actually, I think the cosine is a little more complicated because e to the x, if you take the derivative, is e to the x. If you take the integral, it's still e to the x. So that one, it doesn't matter which one you set up as. It doesn't matter if you set up e as your dv or your u because you're going to get the same result. Whereas cosine actually changes as you take either the derivative or the antiderivative. So in this case, because of the options we have here, e to the x versus exponential function versus trig function, then the trig function actually becomes my more complicated function. So that's what I'm going to set up as my dv, okay? So u is e to the x, dv is cosine of x dx, okay? Next step, find du and find v. So du is going to be e to the x dx, v is going to be sine of x, right? Okay, now I have all my parts. I'm going to write out my integration by parts. So uv minus v du. So notice how my new integral is not so far off as my original. My new integral still has a trig function and still has an e to the x function. It's not any easier. You're correct. So in these cases, you have to do it again. So you need to integrate by parts again. So you need to use this new one and set up another integration by parts. So all I did in the next line was just rewrite my equation. So they're lined up kind of exactly the same as my original one. So this piece that I highlighted here is still the same piece here, but I just rearranged it so it looks like my original one. So they kind of match up. Okay, so now my focus is just on this integral. I'm going to do integration by parts on just that integral. All right, so now my new u is still e to the x, but my dv is sine of x dx. Okay, and then now I take the du and I take the v. So now I have du is still e to the x dx. V is now negative cosine x because my derivative is sine x, right? Okay, now with that piece, with these pieces, I am going to do integration by parts for that. So that becomes e to the uv, so e to the x times negative cosine x, minus v du, so minus cosine x e to the x. Again, you're going to say it's still the same as before. Yes, it is. And this is a good thing. Okay, so now let's see. We're going to have to piece together the whole thing. So if I were to start my equation with what I had originally, my original equation is this. and it equals so many different parts, right? It equals to this, and then including this integration by parts. So let's combine it all together. So my equation was, I started with this integral, right? And this was the first integration by parts. And then this is my second integration by parts, right? So I got all my pieces in there. If you're not sure, go back and rewind and rewatch what I said, okay? And now we're going to clean up the right-hand side a little bit. So we're going to clean this up and say e to the x sine x plus e to the x cosine x minus the integral of e to the x cosine dx, right? So I clean this up. So what I want you to see is now you have algebra, because if you take a quick look, you have e to the x cosine x dx, you have a minus integral e to the x cosine dx. These are exactly the same thing. So right here, the hint is to do algebra. You add this over to the left-hand side, hence creating 2 integral e to the x cosine dx is equal to whatever you have left over on the right-hand side, which is this e to the x sine x, e to the x cosine x. All right. So then again, we're solving for this integral. So the only thing you need to do is divide the right-hand side by 2 or multiply by 1/2. So in one step in my final answer, I am going to multiply by 1/2 on the right-hand side and also factor out what they have in common, which is e to the x. Hence, my final answer is e to the x over 2 times cosine sine x plus cosine x. And then at the very end, put plus c because I'm done with my integral. Okay. This is a special case. It does come up, right? So make sure you do realize that when you have a pairing of each exponential function with a trig function, this is kind of the cyclic cycle of integration by parts. It usually takes at least 2 steps to get the same thing to pop up again. And then using algebra, you either add or subtract the final integral over to the left-hand side, your original integral, and therefore you can divide by the coefficient where we have a 2 here. Sometimes the coefficient is a little bit more unfriendly, so like a fraction. But again, divided by a fraction is not a problem because then the right-hand side cleans up really nicely for you. And that way you have your integral on the left-hand side, getting rid of that coefficient. You have the coefficient now on the right-hand side with your integral answer, okay? All right, next we have a few more examples. As you can see, you now have 3x times e to the 2x. All right, so as we said before, it is much easier to set up the more complicated equation as your dv. So that's why u is going to be my 3x, dv is going to be e to the 2x dx. Right. So then when we take the derivative of 3x, we get 3 dx. And then when we take the antiderivative of e to the 2x, don't forget that 2 comes out as 1/2, and then you have 3 e to the 2x. The hardest part about these problems is keeping track of which ones you take the reciprocal of, which ones do you take the coefficient of, right? So just really try to keep that down, that when you're taking the derivative, the coefficients come out as a coefficient, still the same number. But when you're taking the antiderivative, then you are going to have those coefficients come out as a reciprocal, okay? All right, using integration by parts, we have u times v minus v du, right? And for me, I am going to factor out the coefficients of 3 over 2. So I take that outside. So now I have negative 3 over 2 on the outside and the e to 2x dx in my integral. And that is an integral I know how to do because we already did that over here on the left-hand side, which is going to be 1/2 e to 2x, right? So hence, my final answer looks something like this. And I'm going to clean up having... you don't have to do exactly what I did here. You don't have to factor it out, but this is what I was saying before. It is optional to factor out. If you don't factor out, excuse me, sorry about that. If you do not factor out, you can just keep it as 3x e to 2x over 2 minus 3 e to 2x over 4 plus c, and that's totally fine, okay? All right, number 4 here. Here we have a polynomial function with a trig function. If you're one of those folks that really like to read the book actually has what we call a tabular method, a table method, but it is not super useful to kind of do that because that tabular method is only useful if you have a polynomial function paired up with something else. And it's not always the case. I mean, you have all these other options of pairing up. So the table method is only useful if you have a polynomial function paired up with either a trig function or an exponential function or yeah, pretty much those two. It's not very useful for other cases. All right. So what the table method is doing for you is it is doing integration by parts, but there's a lot of little bits and pieces you have to remember. So typically it actually is not too awful to just do the integration by parts 2 or 3 times until you can get a clean integral. So what am I talking about? Here in this case, I will say that the sine x is more complicated. So sine x is more complicated, hence that is going to be set up as my dv. So my u is to x squared, dv is sine x dx. Hence, du is 2x dx, v is going to be negative cosine of x. Pairing that up in my integration by parts, so uv minus v du, right? And for me, I'm going to clean up a bit of the things. I'm going to clean up the minuses here and the 2, I'm going to take it outside. So my new integral looks something like this, negative x squared cosine x plus 2, and then you have your x cosine x dx. Once again, if you take a look at what's inside my integral, you have x times cosine x. It's not a clean integral that I can work with. Therefore, you have to do integration by parts one more time. So my new u is going to still be my x, and my dv is going to be my trig function cosine x. When you take the derivative of u, it's going to be dx. When you take the antiderivative, it's going to be sine x for the cosine, right? Okay, now we're going to have to make sure I now rewrite the next row of integration by parts. Keep in mind though, you still have this. You started with this, you have a 2 on the outside, and now this is going to be used for my integration by parts. So my next line looks like my original negative x squared cosine x plus 2. Now the new integration by parts, uv minus v du. If you distribute your 2, you're going to get your next line to look like negative x squared cosine x plus 2x sine x minus integral 2 times integral sine x dx. Again, key point. Now this integral, this last integral is absolutely doable. So now I can actually do this one and get my final answer to clean up to be negative x squared cosine x plus 2x sine x plus 2 cosine x plus c. As you can see, the your polynomial function actually went down in power in each of the terms. It started at x squared and now went to 2x and now it goes to 2. It is kind of the derivative as it goes down. All right. So again, if you want to use the table method, it's fine, but there's a lot of little pieces to look at. So if you're comfortable, it is okay. Just remember that that method is pretty limited, and hence that's why we're not going over those in depth in class. Okay. All right. Next problem. This is a very popular problem that shows up again and again. So what Mr. McGurk has suggested is that it may not be a bad idea to kind of memorize this if you want to, because it does show up a lot over and over again. But, you know, it is kind of your choice. So it's really weird because I don't see integration by parts. I don't see 2 parts. You actually do. You have natural log of x as one part, and you have dx as the other part. And now the problem with this then is who to set up as my u, who to set up as my dv. Well, it's actually kind of obvious, because if you set natural log of x to be your dv, you then need to take the integral of natural log of x. And we actually don't have that. That's what we're trying to solve right here. And that's why this is not doable. So that's why you must set up your natural log of x as your u, and then your dx is your dv. And then it becomes much more easy to do. Then du is 1 over x dx. And then if you take the integral antiderivative of dv, it's going to be dx, which is v equals x. Okay. And now if we put it in my integration by parts formula, we have uv minus v du. And that's really awesome because this x and 1 over x reduces out to give me 1. Or, you know, it kind of disappears because there's a 1 here, right? And then so when you take the antiderivative, you get x natural log of x minus x and then plus c. Okay. And again, these are all provable. You can actually take the derivative of your final answer and then see if that gets you your integral back. And it truly does. So it's kind of neat to see how this come about. The thing about these formulas, these functions, is that a lot of times the final answer is a lot more complicated than what we have here, because what in your steps of taking a derivative, a lot of things actually do cancel out. You have the positive and negative pieces and they do cancel out. And that's why you don't see all the in-between pieces. And that's why the integral becomes so clean and so small. And it's hard to picture that, oh, my original function is actually this many terms or this big of an expression. Okay. All right. Last one here, you have sine inverse of x dx. Very similar to what we had before. Because you have a single term here, the suggestion to you is to really let your dv to equal dx, right? And then your u is equal to whatever the function is. So to let your function your u to be the function, and then dv to be this dx over here. And that is what typically works for these kind of cases. Okay, so in that case, we have u equals sine inverse of x, and then dv is dx. So when you take the derivative of sine inverse, you have to use your formula, 1 over 1 minus root 1 minus x squared dx, and then dv equals dx becomes b equals x. Okay, integration by parts gives me u times v minus v du. And now what you need to recognize is this part right here. Your integral now has a single x, and you have 1 minus x squared down here. So because 1 minus x squared, when you take the derivative of 1 minus x squared, it actually becomes x. So recognize that at this juncture, you can actually go back to using u substitution, right? So now over here on the left-hand side, I'm going to tell myself, I'm going to let u be what's in the parentheses, or what's in the square root, 1 minus x squared. Therefore, du is going to be negative 2x dx. Move your coefficient. Remember, step 3, move your coefficient. Negative 1/2 du equals x dx. So now I start off on the left-hand side. I start off with this integration by parts, so I'm going to keep that. But then now I'm going to do u sub with this. So it's going to look like x sine inverse of x minus the integral of x over, I haven't used u sub yet. I'm just rewriting it so it's a lot cleaner. And now in the next step, I'm u subbing this, right? So don't forget that I am u sub, this part is the u, so that's to the negative 1/2 power. And then this x dx got replaced by negative 1/2, that's why it became a plus there, du, right? Okay, so now this is much more doable. I have x sine inverse of x, that's already done, I don't need to worry about it. You have 1/2 integral of u to the negative 1/2 du. Okay, now I can take the antiderivative. So you still have your x sine inverse of x plus 1/2, and now you have your u to the 1/2 power multiplied by the reciprocal, which is 2 out here, and this will reduce out the 1/2 out here. So your final answer should be x sine inverse of x, u to the 1/2, u which is 1 minus x squared to the to the square root of 1 minus x squared, and then put your plus c, your constant at the very end. Okay. Yes, integration by parts is pretty powerful and pretty useful in these more complicated cases. So again, make sure you do go through all the homework problems and speak up if you have any questions or need any confusions cleared. Okay, all right, that's it.